a photo bomb.
They went in for a parent. Actually, would you mind moving down on that? One of those students is getting down. I'm just, yeah, Brady Bradshaw. I sent it down to find you because I wasn't sure if you would. Okay. Well, now that we have firm memory, I want to welcome everybody for Colleen Bove's Honors Thesis Defense. Colleen comes from the Raleigh area. She went to Leesville High School. While here at College's she participated in study law at the University of Southampton at the National Geographic Center as a very young sophomore. And then later on she did study law at South. Her poster of her presentation was awarded first place prize at the Denver College and she recently presented her work also at the Colonial Academic Association conference. And I'd like to introduce members of the committee, Dr. Rob Whitehead, who is the co-advisor, Dr. Satterley, Dr. Allison Taylor, and Dr. Hilliard, who is the honors program director. I thank all of you for coming for and without further ado, please.
Thank you for the introduction. And thank you guys for coming. And today I'm going to talk to you about my undergraduate honors thesis entitled The Effects of Seawater pH on the Gastrovascular Cavity of the Coral on Asphere cavernosa. Can corals counteract the effects of ocean acidification? So first off, a little bit of background on what ocean acidification is. So we all know that there is an increase of CO2 being released into the atmosphere, mostly from anthropogenic sources. And this is causing an increase in the partial pressure of CO2, which is driving more CO2 to dissolve into the world's oceans. Once in the oceans, the CO2 is reacting with water, and it is forming carbonic acid, which has a short life because of the actual chemistry of the seawater. And then it goes on first to produce bicarbonate, and then some also goes on to produce carbonate, both of which by losing protons. So there's a total addition of 2 protons if the equilibrium goes all the way into forming carbonate ions. So some of these protons, however, from the first loss of a proton, goes on to react with the available carbonate ions in the seawater, and these are increasing the concentration of bicarbonate in seawater, which is also decreasing the pH of seawater, and of course reducing the concentration of carbonate in the seawater, which is causing a reduction in the saturation state of aragonite, which is an index of saturation measured based on the concentrations of calcium and carbonate and the solubility. So there are two calcification equations that can be written. First off is the chemical equation, where calcium and carbonate are reacting to form calcium carbonate, which is a solid, and that is the skeleton of corals. And then from more of a physiological standpoint, we have calcium and bicarbonate forming calcium carbonate, CO2, and then this, of course, is water. So what we see from these two equations, if we look at the top one, we notice that there is carbonate in the equation. And so if we're reducing the concentration of carbonate in seawater, then theoretically we'll see some sort of impact of saturation state and the reduction of calcium carbonate influencing the availability for calcification. And in the second equation, we see more of an influence on these extra protons being created, causing a decrease in pH, thus affecting the calcification of the corals. So various studies have shown that there is this relationship between aragonite saturation state, seen here on the x-axis, and study by Langdon and Atkinson from 2005 shows a linear relationship that when saturation pH and saturation state are decreasing, we see a decrease also in calcification rate. Other studies have been performed that show this similar trend, and others have been performed on more sensitive corals, and they've shown different responses. Some corals don't even show this sort of linear relationship when looking at aragonite saturation and pH in comparison to calcification. So now that we've kind of explained how corals are overall responding with this aragonite saturation and pH, we're kind of viewing corals as a black box. So let's take a look at the actual coral itself. So here is a coral polyp similar to in appearance to the one that I used. And what we see it actually has an exoskeleton, but the tissue is on top of the skeleton, as seen here. So the skeleton is not in contact with the external seawater. So first up here we have the oral ectoderm and endoderm. And the green is the oral ectoderm, and it caves in at the mouth, and it forms this cavity, which is the gastrovascular cavity. Also seen right here in this. Here again we have the oral ectoderm, oral endoderm, and then the gastrovascular cavity. And so this is our top layer of tissue on the coral polyp. And within the top layer of our tissue, the oral layer of our tissue, we find the zooxanthellae, which is a symbiotic algae within the tissues. And these are very important in corals because we know that they are both assisting coral functioning, and they also provide receive protection from being within the coral tissues. So that's the oral tissues, and then we have the aboral tissues down here, which again are composed of the aboral endoderm and the aboral ectoderm, also known as the calicoderm, which is down here. And so the calicoderm is the layer that is the closest to the skeleton and actually acts to produce the skeletons, which is seen down here. So it is important to look at that calicoderm in relation to calcification. And we know that calcifications of corals occur in this calicoderm, which is also seen here. But the exact model is not well understood. But here we have one of the most accepted models for bringing in ions for calcification. So what we have is a calcium coming in to our calcifying medium, which is here. And it combines with the carbonate to produce the calcium carbonate precipitate, which is the skeleton here. But when we do this, we also are left with protons in the system. So there is a proton pump that, as the calcium comes in with a positive Q charge, 2 protons are able to be removed totally at positive Q charge as well. And we see that since the gastrovascular cavity is the most proximal area to where the calicoderm, or to where calcification is occurring, that these protons are most likely being placed into this calicoderm, or into this gastrovascular cavity, where they are also altering the equilibrium of the carbonate system, because this is again just seawater that has been brought inside the gastrovascular cavity. So it's going to have similar equilibria to the carbonate chemistry and the external seawater. And it is thought that this is potential to aid in the photosynthesis of corals, because more oxygen and CO2 or more CO2 being added into the system, aiding and assisting in more photosynthesis. So now we have a general idea of how the corals are functioning and producing their skeletons. And it brings up that a lot of people haven't focused on the actual internal chemistry of the GVC in relation to corals. So one study here, back in 2012 by Agostini et al., measured the oxygen concentration, first just at the mouth of the polyp, and then about a millimeter within the gastrovascular cavity. And when they measured it in the dark periods, they found a decreased concentration here, slightly within the gastrovascular cavity, and see that the oxygen concentration again increased between 300 and 400 micromoles per liter, which again is supersaturated in relation to the external seawater. Several other studies have looked at the internal pH, the GBC pH of corals, and here we have a review that compiles several of the studies. But one study by Al-Harani shows some data here. This is the surface of the polyp again, and here is within the gastrovascular cavity. And what they showed is in the light, which are these light bars, that the pH within the GBC increases, and it comes well above the external pH. Both of these studies were done at a normal pH of about 8.1, 8.2. And as you can see, the pH rises up closer to 9 in the light. And then in the dark, with these gray bars, we see that over time the pH decreases, and this time it goes well below the seawater pH, closer to 7. And from what we see of these studies that have been compiled together in this review, is again, we see light is significantly higher than our seawater pH, while in the dark we see that it is decreasing. In the dark we're seeing pHs from about 7 to 8.1, and in the light we're seeing from about 8 to 9.2, regardless of species. So from all this data, they analyzed solely the normal seawater pH, and some of their runs were fairly short. And so from this introduces the issue of ocean acidification again. We know that we have seen that the corals are able to function and produce their skeletons under normal conditions, and under these normal conditions, it's been measured that the gastrovascular pH goes from a very low pH, around 7 sometimes, up to a very elevated pH, almost close to 9 at other times. So since they are able to perform their everyday functions with these large diel shifts, how is changing the ocean chemistry of ocean acidification, which is expected to have comparatively small changes in seawater pH, how is that going to affect corals really? So for my study, I wanted to look at inside the GBC and see how it was changing, because it seems to play an important role, and since we're seeing these large shifts every day in the pH, then I wanted to look at that by adjusting light and dark, and then as well adding in the aspect of ocean acidification by reducing the seawater pH. So I came up with 4 hypotheses that I wanted to address in my research. And the first one is about oxygen. It's more of a general hypothesis, analyzing how the oxygen is changing within the GBC. And we know that with photosynthesis occurring, we're going to be reducing the CO2 and increasing the oxygen from photosynthesis of the zooxanthellae. And then again in the dark, since we will have solely respiration, we will be removing oxygen from the environment inside that GBC. So we should again see a decrease in the oxygen concentration. Next, it was a very similar approach to the oxygen, where we just wanted to solely look at how pH fluctuated from light and dark within the GBC, because we know that in the light we have calcification and photosynthesis, which theoretically should be driving the pH within the gastrovascular cavity up. And then again in the night, with this much slower calcification and solely respiration, we should see a decrease in the pH. Next was looking at how that GBC pH is responding to changes in the external seawater pH. So I wanted to look first in the light and then in the dark, because the different processes, and just focus on GBC pH response to pH reductions. And finally, the purpose of this all is to tie it in with calcification. So while measuring the GBC pH, I also performed calcifications at control pHs and to reduce pHs. And I wanted to see if I could see any sort of relationship there as well. So to tackle these questions, I looked first at just measuring the GBC, pH, and oxygen. So in the dark, I was expecting solely respiration, and so I was using dark conditions how that would affect the GBC with oxygen and pH. And then again, in the light, I wanted to see GBC and pH and how it was changing with that addition of photosynthesis. And then I altered the seawater pH in order to simulate some expected effects of ocean acidification. And then again, lastly, measured the calcification at a control 8.2 pH and then 2 reduced pH values that are somewhat expected by the end of the century. So to start with, I wanted to make sure that my seawater was not adding any additional confounding variables to my calcification rates. So I had some seawater that had been collected offshore at Gulfstream, and they were in these carboys, and they were filtered with 0.2 micron filters in order to remove particulates and 99% of bacteria. And from there, they were all significantly reduced pH. They're all around 7.6 pH naturally. And after they were filtered, we bubbled them with CO2-free air to raise the pH up to the desired pH levels, and we ensured that all their total alkalinities were approximately the same. Once I had my water filtered and set up, I began performing experiments. And so I took my small colony of Moncaster cavernosa, which you can see there, and I placed it in a dish with constant stirring. And it was in a heating bath to maintain the temperature of the water, but I omitted it from this photo for clarity. And it was placed under a microscope, and I placed either 100 micron or a 500 micron. I started with 100 micron microelectrodes, and then eventually switched to 500 micron microelectrodes for the pH. And I placed them with using a micromanipulator inside the mouth of the coral, as seen here. And here's the microelectrode. And from there, I adjusted light levels. So I had a light system set up where I could turn the lights on, and it would go to about 360 microeinsteins per meter squared per second. And also I constructed a dark hood that I was able to use and to isolate the system from the light and have as dark conditions as possible. And then from there, to maintain my seawater pH, because it would rise due to photosynthesis, I would bubble in CO2 air into the system whenever I needed to. So just to remind you, my first hypothesis deals with the oxygen concentration in the GBC in light and dark conditions. And so you guys can see here are two images of my coral Moncaster cavernosa. So what I found in the light was, again, that high elevated percent saturation. So I measured a micromoles per kilogram and converted to oxygen saturation. And then here we have time. So in the light, I have that elevated saturation, and within about 6 minutes of the lights being turned off, the saturation dropped down to about 0, which was shocking. And then again, with the lights being turned on, it only took another 6 minutes for it to rise back to that maximum saturation that we saw. And just to give you guys a reference, the earlier study measured about 300-400 micromoles per liter, and my maximum values were at about 900 micromoles per kilogram. So elevated compared to theirs, but still super saturated. And so from this, I was able to confirm that my results were in agreement with what Agostini had found when he measured inside the GBC and measured the oxygen. And again, we saw that huge decrease down to 0% saturation in the dark, suggesting an anoxic environment. And I have done a measurement that through the night with oxygen, and I've seen that the saturation remains at 0 through the night. And so this brings the question of what's happening during those dark periods, as well as the potential for that corals don't actually have to pump between the external environment constantly through the night. So hypothesis 2 was similar to the first one, but this time I was measuring the pH within the GBC in response to light and dark. And so here we have time again, and this is the GBC pH. The dotted line is my external pH. The solid ones are the GBC pH. And so this is a little bit of hypothesis 2 as well as 3. So here is an external pH of 8.2, which is about a normal pH for these corals. And we found that in the dark, there was a significantly reduced pH of 7.6, and then when the lights turned on after about 20-30 minutes, we reached a pH within the GBC of about 8.7. And this is what we expected from previous results, as well as our knowledge of how photosynthesis is affecting the system. And in the dark, again, or in 7.9 pH, which is one of my selected pH, we saw the same response of increasing with light. And then again, even at the 7.6 reduced pH. But these are only one trial that I have performed, so I have compiled a table that shows a combination of all of the runs that I have performed, and it's a total of 3 runs at 8.2, 3 at 7.9, and 3 at 7.6 pH. So what we see here is looking at the maximum pH, which would be under light conditions. We see that they're all about 8.4, and so they're not very different. But in the dark, we see that it appears that the one at 7.6 is slightly reduced, but they're statistically not different, since you can see that there is a similar variation, and also they've been analyzed to not be different. And what this is telling us again is that from the GBC pH is dependent on the light quality. So overall, we see the pH increases in the light, and it comes well above the seawater pH. And then again in the dark, it comes well below the seawater pH. And we see that the decreases in the GBC pH below the external seawater in the dark was much greater than that seen under the light. And hypothesis 3 is dealing with, again, how the GBC pH is changing with external seawater pH reduction. So first I performed this in the light, and we have time, and then pH is on the y-axis, and my black line is my GBC pH, this blue bar is my 8.2, this orange bar is 7.9, and red is 7.6. And so I placed the coral in a water dish, and I measured the GBC pH, and after it appeared to have a stable reading, I reduced the pH, and I did this to 7.9 and then 7.6%. And afterwards I analyzed this, and it does not appear to have the external pH reduction does not appear to have any significant influence on the GBC pH. However, when this was performed in the dark, I saw that as I reduced the pH, it appeared to also reduce the GBC pH. And this is the only run I was able to do in the dark. So I'm not positive on this, because as you can see, this value here in the 8.2 was around 7.5, and after the entire experiment it got down to about 7. However, in my previous experiments, I found that the So I performed 3 calcification incubations over a 24-hour period. And the first one in each one was always at 8.2 control pH. And then the second one was performed immediately after with about an hour of time in between for it to sit in the reduced pH, seawater. And then it was allowed after the second incubation to sit overnight in the dark in this reduced seawater pH. And then in the morning, after 15 hours after the first incubation, it was placed again for the third and final incubation. And all 3 of these calcifications were performed in the light. And so the first time, there was 2 that were performed with all 3 of the pH, external pH being at 8.2. And then also I performed the same series with these 2 second ones being at 7.9, and then a third one at 7.6. And so, as I said, they're all in the light, and I measured the changes in total alkalinity as a measure of calcification. So first, looking at my control series, I found that there's no statistical difference from the 3 calcification incubations, suggesting that there was no issue in my methods causing a decrease or increase in calcification rates by method alone. And then I looked at the calcification rates performed under a 7.9 reduced pH, and I found that these 2 calcification rates were not statistically different, as well as they were not different from our initial calcification rate. And finally, I looked at the calcification rates of the corals under a 7.6 pH, and I found that the 2 7.6 pH calcification rates were similar, or were not statistically different, but when compared with the control, they did prove to be statistically different. But I looked at this control rate, and I saw that its rates were much higher than my controls from my entire control series as well as my 7.9 control. And in fact, these calcification rates were almost identical to the calcification rates I was receiving for 7.9 and 8.2 previous runs. So I do not think that these are actually statistically different, but it was a cause from this oddly high calcification rate at the initial. So as Langdon and Atkinson had compared calcification rates to pH, I also wanted to do that to see if I found any correlation. And so up here, I measured the calcification rate against the seawater pH, and I did not see any significant correlation here. But since I measured the GBC pH throughout these calcification incubations, I thought that there may be some sort of correlation that we can see within the GBC because it is more direct to the calcifying fluids. And again, we have the GBC pH and the calcification rates, and there is no correlation again with this plot. So overall, we found that the calcification rates were not influenced by reduced seawater pH, my small colony of non-patching cavities, only in light conditions. And there was no difference between reduced pH as well as the amount of time exposed to reduced pH. And again, there's no correlation in any internal or seawater pH with the actual rates of calcification. And finally, I was able to suggest that in my study, in my specific coral, which is a fairly hardy coral, that it was not affected by the reductions in seawater pH down to 7.6. So just to recap on my hypotheses, first was the oxygen, and I thought that I would see an increase in oxygen in the light and a decrease in the dark, and yes, I saw this, and it agreed with all the results I had seen previously. Second, will my pH increase in the light, increase in the dark? Yes, it was similar to those shown in previous studies with other corals. And then third, gets a little more interesting. I saw a decrease in the GBC pH in response to reductions in external seawater pH. have that the GBC in the light is significantly elevated compared to seawater pH. When external pH is reduced, we do not see a reduction in GBC pH. And then this is different from the dark, where I do see a reduction in pH. But this may be, this needs to be looked at again, because I, again, only have one experimental trial of this. And then finally, because of the knowledge that there is potential that the GBC pH is sensitive to the external pH reductions, it's important to perform these calcifications. Maybe consider times of dark. So maybe performing these calcifications in the dark, or doing a method where we incorporate more than just light calcification, because this could be, the dark times could be when corals are most susceptible to these reduced pH. And with that, I would like to thank everyone from my committee and all the UCW faculty, and especially Dr. Schwab for being my mentor through this all, and also all my funding sources that have paid for my project and sent me on conferences. And with that, I will open up the questions. Yes.
Do you think you would see more changes in calcification rates if you did your studies for a longer period of time?
Changes between a control pH from a reduced pH, that is a possibility, but I measured my, the reason I did those two different pH, or the two different times with the pH, was because I was expecting that my first calcification rate, it may not be influenced by the reduced pH, but the second one in the time series, it had been in that reduced pH through the entire night for about 15 hours, and I should be seeing some sort of influence if that was an issue. But there is a possibility that if I had kept these corals in a reduced pH for a much longer time, I could be seeing an influence.
Do you know whether these particular corals use carbonate or bicarbonate?
There is no way to tell for sure whether or not corals are utilizing bicarbonate or carbonate from the external system, but from once it gets into the calcifying fluid, it eventually is using carbonate. So I'm not sure 100% on if there's a specific one that corals use.
There is no known transporter in carbonate from membrane. All the instructional evidence for molecular techniques as well is that bicarbonate is the molecule. And then inside the cell complex, carbonate.
So using bicarbonate as a saturation index idea really works.
Not mine. That is sort of the dichotomy between physiology and chemistry.
So, clarify Dr. Willie's point, and you said it in your talk. What happens with pH and saturation state when we're having ocean acidification?
So when we have ocean acidification, how does it
Go back to the water.
There,
So if we have ocean acidification, how is it affecting the saturation index? And, sorry.
so the relationship between pH and saturation state on your, so her question was the relationship between saturation state and calcification, but equally pH is dropping at the same time.
Right, so
So you plotted yours versus pH and Langdon and Atkins, and plotted theirs versus saturation state. But is there any difference in those two things?
okay, so saturation state is the measurement of the carbonate and the calcium ions, and then pH is are, though the seawater stays at bicarbonate because of the chemistry of the sea, we are still producing more protons overall, which is reducing the pH. And since we're adding protons into the seawater, those are also reacting with carbonate ions. So as we are adding CO2, we're increasing proton concentration, which is dropping the pH, and we're taking out carbon